Pleasure to welcome you to the fourth edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP Lecture Series is a pro bono initiative led by Dr. Partha Mishra and Professor Subhadeep Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The Pan IIT Lecture Series on geotechnical engineering consists of 6 talks, which have been delivered by the pioneers in the field of geotechnical engineering from different IITs. The following lecture is the first talk of the session 1 of the lecture series. This lecture is on modeling of cyclic responsive soils, theory and application, which will be delivered by Dr. Subhadeep Banerjee. Subhadeep Banerjee is currently serving as the Professor of the Department of Civil Engineering at Indian Institute of Technology, Madras, India. He received his PhD in Civil Engineering from National University of Singapore in 2010. His research interests include seismic soil foundation interactions, cyclic behavior of geomaterials and finite element analysis of complex dynamic problems. Besides, he is also an expert in constitutive modeling of soil, special emphasis to the transient dynamic behavior. At IIT Madras, he has formed 3 research groups to study the cyclic characterization of various types natural soils, improved ground, landfills etc., and development of constitutive models of soils emphasizing on their performance under seismic loadings, and application of fundamentals of dynamics to various complex soil structure problems such as tunneling, base isolation techniques, plate anchors, retaining walls etc.
We'll study a few natural and modified geomaterials, how they behave under cyclic loading mostly, and then what are the difficulties associated with these materials? For example, how to measure, the simple one, how to measure their compacted density, how about the static strength of those materials, their applications and how difficult to apply them, and can you model them, at least approximately. That's what we have today. So we start with this, the simple among all is the natural and cement treated marine clay. So as we all know that our coastal India and many parts of the world are thick and thin with marine clay, and they are characterized by the high water content as well as the high compressibility. To reduce those compressible nature or to gain in strength, sometimes we do cement treatment, right? So now, once we do the cement treatment, it was kind of assumption that it is fine against any kind of earthquake or wave loading. But if you see this particular case, which is a dike in Japan, it's constructed over the cement treated. I mean, it's basically DSM columns, deep soil mix columns, and it's got some kind of significant damage during the 2011 Fukushima earthquake. So it may not be ideal or appropriate to assume that just the cement treatment is kind of a fine for any kind of situation under dynamic loading. Now, before critically examining, let us see what we know. We know that soft clays or clays in such has a nonlinear stress-strain relationship. At the same time, its stiffness degrades with cycles. So if you go on increasing the number of cycles from first cycle to 10th or so on, its stiffness reduces. These are all very well-known facts. This is also another very well-known fact, or kind of a design protocol, is that shear modulus, or let's say normalized shear modulus, generally reduces with the strain and the damping increases with the strain for obvious reasons. So these are all very well-known facts. Now, how we established all those? These are the equipments which we have in our IIT Madras. It's resonant column apparatus, which is for the very medium to small strain range. And then this is cyclic simple shear, and this is cyclic triaxial. Cyclic triaxial and cyclic simple shear are ideal for medium to high strain range. Only difference in cyclic simple shear, we could able to see the actual principal stress rotations, whereas in cyclic triaxial, we will not be able to do principal stress rotations. Of course, all the machines are fitted with the Bender elements, which measures the shear modulus under very, very small strain range. So these are the weapons if I call it, to need to analyze all these studies. Now, if we directly go to the study, the experimental program, which we have carried out in IIT Madras few years back, it's with varying cement content. The soil, the clay will be mixed with a varying cement content, starting from 0 means a pure clay, then 2.5%, 5%, 7.5 to 10. Then we vary the frequency of loading. We vary the strain. We study from the small strain to the quite high strain of 1%. We have a fix on the number of cycles 100, then confining pressure. We used our locally available marine clay with 54% of liquid limit. Roughly, it's basically quite a compressible in nature. Then first thing is just we did the ground preparation. That means we just vary the cement content and we do some resonant column to test out. And we saw, as we expect, that if you increase the cement content, the shear modulus increases. If you increase the confining stress, shear modulus increases. If you increase the curing stress, obviously shear modulus increases. So all this thing is all known fact and you expect, but this gives us a platform that our sample preparations and testing conditions are appropriate. Now we did the cyclic triaxial test on cement treated marine. We did it for a series of different conditions, but I'm just showing a typical one. If you can see, the blue line is for the first cycle, the red line is the 10th cycle, and black line is the 100th cycle, and there is a gradual reduction of the shear modulus as you keep on progressing the number of cycles. Now, being said so, we just compare with the pure clay situation. Now, this is the comparison is done based on a well-known formulations by entries, which says there is an index which terms as degradation index, which is nth level, nth cycle shear modulus to the first shear modulus. And then if you compare that and you came up with a kind of a logarithmic plot, and if we see there's a degradation parameter, and as you can see that the red line is of course natural Chennai marine clay, which is having a very, very strong degradation behavior. That means with number of cycles, it reduces a lot. But obviously in cement treatment, you see a reduction in that the degradation behavior, but it's not ignorable. I would say it's not a completely negligible. It is also showing very significant degradation even in the cement treated soil. So assumption that the cement treatment is a cure for all may not be the correct one. So now we did, because it's a multiple thing. It's you cannot really attack one of the parameters. You have to see multiple facets of this behavior. So as we have done a 3D plots, and we have seen that the amount of all the factors like frequency, curing stress, curing days, cement content and the strain are the obviously predominant factors. And that's what we expected as well. But before going into the further, you see there is an interesting feature. Like at the lower cement content, if you see that the degradation is very obvious, but at the higher cement content, degradation is of course reduced, but it is also a function of the frequency of loading. Now, how frequency of loading plays a role, that's we just studied. We have studied various things. I'm just highlighting here the pore pressure response. If you see the pore pressure generation, like this red points, this is the stress by strain, deviated stress by strain. And if you see the red points is basically 0.5 hertz, and the blue points are 0.1 hertz, very slow. Now, if you compare the pore pressure development is 100 days, so pore pressure development is there. So you can see, just take any of the strain. Let's take the bottom one. The solid points corresponds to 0.1 hertz. The hollow points corresponds to the 0.5 hertz. And as you can clearly see, the 0.1 hertz, the lower frequency, is actually leading to higher development of the pore pressure. And it is consistent for all different types of strain. If you see at the 1%, the highest one, see the solid point in the black is at the top. And then this is the hollow points are here, somewhere there. So consistently, we are seeing that the lower frequency is causing higher development of the pore pressure. The reason being the fact that in the lower frequency, the particular sample is sustaining the load for the longer duration. So it is slowly going down and slowly going up. So the particular sample under ambient condition is experiencing the load for a longer duration compared to the higher frequency loading. So that's one of the hypotheses we made from this analysis, which is very important. In fact, you see this direct application is there in the liquefaction. People have already commented that under low frequency, low to medium frequency earthquakes, the chances of liquefaction is more because the development of pore pressure is more. So it's kind of similitude to that type of logic. So now we did different conditions check with the effect of different higher confining pressure and then higher cement contents. And as you can see that confining pressure has quite significant effect over the modulus, but it really doesn't make much difference in the damping ratio. Similar thing we can see over the cement contents as well. Now, with that idea, we try to come up with a simple constitutive model for cyclic loading in clay. So this is the idealized hysteretic behavior. So this is the hyperbolic backbone curve. We just follow a hyperbolic equation. And then the cyclic behavior, it's modeled using the Masing rule. That means the loading. So this is backbone curve, it goes to the first loading, then first unloading, and then first reloading. So first unloading and first reloading, we followed the Masing rule, which is very common for the metals. And then we model the stiffness degradations. As the time progresses, as the cycle progresses, your modulus is changing, which is obvious as we have seen in our previous experimental studies. So with that, we come up with G by G max versus shear strength curve, and then we are not happy with just our test results. These black points are our test results. Then actually we compare with all sets of different people over the years tested on clay with a different plasticity index and different testing protocols. Now we are happy that our things is comes somewhere in between. Of course, there is a band. And our prediction, the red line is our predictions is somewhere within that line. So again, we keep on studying our degradation behavior. We saw that the degradation, as we have seen that 3D plot, that the degradation is a function of strain, PI, over-consolidation ratio, and the frequency. And if we try to match that, if we come up with that formulations, and we try to do a simulation and compare with the experimental data. Of course, we didn't, to make ourselves happy and confident about our model, we didn't choose our data at all. We selected established, very well established data on with varying these parameters, and we used the computed equation as per our development, and we saw it's matching fantastic. I mean, we were more than happy. In fact, here we used 3-4 different sets of data reported by Professor Subhadeep, and then we saw that our models is to some extent getting very positive results. So this is for the natural clay. So with that idea for natural clay, we actually ventured into the cement-treated clay models, and we saw that okay, apart from the regular factors which are there for the natural clay, for cement-treated system, we have to add a cement content as well as the curing days as two governing parameters. And then we try to compare with the experimental data with our predictions. Of course, you will not get as good as it is in the natural clay, but still, I would say we are generally happy with the performance, if you ask me. What about the contaminated soil? That means if you, like so far we have seen for the pure clay and cement-treated clay. Now if we add up some kind of pore fluids, we change the pore fluids, how is it? So that means we test. We can do many things, but we do just a sodium chloride. Actually, we have tried with calcium chloride also, but I'm not sure because there's some problem happened because of the corrosive nature of the CCl2 in our equipment. But with the sodium chloride solutions under different confining pressure, of course, because of the development of the diffuse double layer with pore fluid with the sodium chloride, the general stiffness is more, the shear modulus is more. But one thing is we noticed is that the degradation, the nonlinearity with the change in pore pressure and changing the from 0.4 m to the 1 molar solution, it's even more significant. You see there's a sharp decrease in the modulus as you keep on increasing the shear strength. So that's one of the things we noticed. And with that experimental behavior, then we try to come up with a constitutive model for the contaminated soil with a different pore fluid. And we have seen that with a difference in the pore fluid dimension. So what we have to do is you have to simply improve the factor in the term, which is called concentration factor, and we have tested for 0.141 and other thing. And you see Q over MP dash over 2 to the power delta, it's actually, this is very similar to your typical critical state framework. Those who are working in critical state, they know that Q is equal to failure stress equal to failure strength is Q MP dash over 2 to the power n. With similar idea, instead of when we use a delta, that delta is a function of the concentration of these saturated solutions. And then if we do that, we got a quite reasonable match. In fact, we were very happy that we could able to match the hysteretic behavior. You see, it's not easy to get hysteretic behavior match for any soil, let alone if it is a different pore fluid. Not only that, we try to establish how the anisotropy, because you see, one of the questions we always ask is, we are doing all kind of thing in the isotropic situation, but in field, it's actually the anisotropy, right? So in anisotropic situation, and of course, it is not a material anisotropy, it is a stress-induced anisotropy, I would say. So basically, in our triaxial system, what we did is we keep on first consolidating the soil under an isotropic condition, and under that anisotropic K line, we apply the cyclic loading. Now, how to choose the anisotropy? That was a key issue. So one means Kc is one means basically sigma 3 is equal to sigma 1, which is isotropic. And then we choose the 0.55 is the K0 condition, absolute K0 condition. Then we choose a in between 1.67. You cannot go less than 0.55 because it is not ideal, because it's not less than ideal. Less than K0 condition is more like a active earth pressure condition. We are not studying any active condition in the soil. We are just boundary, our analysis boundary is the within at rest. Now with that, we try to do the degradation. We did a detailed study, but I have here shown you the degradation part of it. And with the degradation, we saw that the values, you see this red line is for the isotropic, then the blue line is for the Kc is 0.67, and then finally the brown line is 0.55. And you can see the degradation is very, very significant if you are talking about that higher stress-induced anisotropic. And it's even more complicated or interesting if it is a frequency is less, and strain with a higher strain, it is very significant as well. So with that, we'll go for our next part of the lecture, where it is we go with the particulate rubber sand mixtures. We all know the SRM can be used, the sand rubber mixture can be used for various applications. It's generally used to reduce the active pressure behind the wall as a protective cushion, can use for the shore protections, can use as a backfill, lightweight backfill. But what previous studies suggested that it is a lightweight material, it has a low liquefaction potential and high damping ratio. So different applications, and then recently it used as a backfill for the pipe, also pipe materials. So we try to do that. We started this work a few years back, and we are still doing this. I'm not saying we have concluded a big time, but we are still working on it. So we started. So if you compare the rubber, it's like a little finer than the little coarser than the sand, and it's more or less uniformly graded. And this is the typical figure. And then how to estimate? First thing we encountered the problem is how to estimate the density, obviously. Because regular vibratory table, which ASTM is suggesting, it's not working because but the density of the mixture increases with increase in surcharge. Not only that, if you remove the surcharge at the end, the density immediately reduces because it tried to dilate out. I mean, its volume expansion happens. So what is the best method? So that is the first question. So we tried Proctor and then we tried a mini Proctor. In fact, Proctor's mini compaction, which proposed by Sridharan in way back in 2005, is a classic geotechnical paper where I think it seems it is in a mini Proctor, it's kind of ideal. Now we did the direct shear as usual, direct shear test for the questionless material. Now, direct shear test result shows a very interesting thing. In fact, we compared the friction angle proposed by us as well as the proposed by others all together in this particular plot, and the green points is us. So one of the things we first noticed is, and which is expected, that as the rubber content increases, the friction angle is reducing. Obviously, if you have a pure sand, your friction angle is definitely high. With rubber, you are reducing the friction among the particles, so you end up having a low friction angle. So that is a positive as well as a negative. We'll see when it is positive, when it is negative. Before going into that, we saw that we did a bit of microstructural study on this rubber sand thing. If you see that, and we also try to benchmark with the fly ash, we saw that particulate rubber observed to be having high rough surface, because it's shredded in a workshop, so it's not a very smooth surface one. The interaction between rubber and sand is much less compared to the rubber and fly ash. In fact, we did a follow-up study with direct shear with rubber and fly ash instead of rubber and sand. There, the reduction in friction angle it's negligible actually. That's the thing which we haven't studied in detail. We'll study in future, but that's for your information that if you have instead of rubber, if you use the fly ash, it's actually not bad because fly ash. What we understood is fly ash particle size is small, so it is nicely fitting within the rough surface of the rubber. So that's why the interaction in the fly ash is much more compared to the rubber, compared to the sand with rubber. So with that, with basic understanding of its material engineering properties, we thought that whether it can be used for base isolation technique. Now, you may wonder what is suddenly the base isolation is. So base isolation is basically, it's two parts. One is you want to lengthen the natural period. So if you use it is as a backfill material below a building, you want to increase the natural period. Why? Because it will reduce the base shear, obvious reason. But the problem is, as with increasing the rubber, the bearing capacity is reducing. That means the angle of internal friction is reducing. You want to damp out the vibrations so that it will reduce the displacement. The deformation has to be reduced because your material is not strong enough anymore. So you have to balance it. Lengthening of natural period means it is a positive side. If you reduce the friction angle, your strength is reduced, so natural period of the medium is increased, which is good. But as you make it softer, the problem is the structure on top of it will deform more. To reduce that, you have to have a high damping. And the rubber kind of provides both. So if you see the peak friction angle, obviously the deviator stress, again the same direct shear test, you see that it is reduces, so it's 10%, 30%, 50%, very significant reduction. And as the peak strength increases in peak strength with reduction in peak strength in increasing rubber content, lengthening period is happening. At the same time, you are getting an increase in damping. Now, damping in rubber, why you may ask that how the damping is increasing? damping in rubber is actually having two components. One is coming from the friction between the particles, as well as the rubber. Now you have to imagine it's not like a sand. Now the rubber is a deformable material. So rubber is actually deformed. So when you have a 10%, 30%, 50%, as you keep on increasing the rubber, the damping is coming only from the deformation of the rubber, not from the friction. But when you have a 0% rubber or a very small percentage rubber, significant or the majority of the damping is coming from the frictional component of it. Now, what we saw here is the 10% to 30% mixture is the ideal, where you get the optimum friction angle as well as the optimum damping. Between 10 to 30% of the mix, 10 to 30% of the rubber, if you replace sand, you will get the damping component both from the friction as well as from the deformation of the rubber. So now we try to apply that in the actual field cases, or we start with the lab, then we go for the field. But the question always we ask that what is the static stability, because we have already established that, or we have seen that with SRM the angle of internal friction is reduces, so static bearing capacity is reduces, so settlement we expect it to be more. Why not you use a geogrid layer to control the settlement? So basically we came up with a simple lab test where you have, this is the natural soil and this is the GBI, that means that sand rubber mix, and it is reinforced with a couple of layers of geogrid. If you do that, you see this is the pure sand. Obviously, if you don't have a geogrid, it will have it much more. But as you increase the layer of geogrid, single layer geogrid and double layer geogrid, you will get adequate bearing capacity with the reduction in the settlement. So now what about the numerical model? So we did the numerical model of the same thing, and we apply the earthquake excitations of the same model, the numerical simulations. And as you can see, the seismic settlement part also same thing. This is the with GBI and this is the without GBI. So without GBI is slightly less because it's a pure sand. With GBI but no geogrid is the red one, where you see that as you have forcefully reduced the angle of friction, its settlement is more. But as you keep up increasing the number of layer of geogrids, you are getting very less seismic settlement. In fact, we have seen that the second is the two-layer geogrid is enough because there is not significant increase between two layers to the three layers. So reinforcement of two-layer geogrid is perfect as per our study. So now we did the shaking table test to understand our hypothesis is correct. So this is our IIT Madras heavy testing lab, where we have a 3 meter by 3 meter shaking table, where we mount our laminar box of 1.5 meter by 1 meter by 1.2 meter, and then with a scaled earthquake motion we will apply, and then we have the soil is here. Then we put our this GBI with geogrid layer, and then we created a scale model of the structure. It's a multi-story structure. We varied different things. I'm just showing one typical picture, and then we have the input accelerations. And what we saw that without GSI, this is the story. We measured the story drift, and with GSI, it's a very high story drift. The amplification is very high as you keep on increasing the number of the stories. And with SRM GSI geogrid, you get a significant reduction in the amplification. In fact, you get a de-amplification. So the waves are not getting transferred at all to the higher stories. Here also same thing, it's an interstory drift. You see without GSI, we are having close to 2% of the interstory drift. But as you keep on adding the SRM geogrid, you reduce, in fact, it is reduced below 1% interstory drift, which is very within the prescribed limit. Now, with the scale model done in the lab, we transfer that to the field. So how we are going to do that? So we studied the ground vibration propagation in the field. So what is that? See, this is the concept which earlier people used. In fact, we saw a paper in 2018 published on the rigid block isolation system. So you prepare a concrete block. So that idea gave us that energy distribution. Here, the energy distribution of the material damping is ignored. It's just a rigid barrier system. But we thought that why not we use the SRM instead of this concrete block. So what we did is there is a ground wall. So this is the layer and this is the vibrating block. So this is the vibrating block and how much the wave is transferring with and without this our proposed GBI system. So we choose a site near Chennai, and it's a typical industrial zone where a lot of compressors, generators are things, a part of the power plant. And city administration proposed to construct 3 mid-rise building complexes in the site. So ground vibration is expected to a problem during the construction. So feasibility of GSI bed we started, and this is the typical soil profile. As you can see, top layer is the loose sandy soil. So which is again, it can easily carry the vibration further. So that's how we did. So this is the concrete block where we create the vibration. It's a typical vibration. It's same setup of the block vibration test, if you ask me. Then we constructed the footing on the GSI bed, and we have a heavily instrumented it with accelerometers on top and on the sides, a series of accelerometers. And then we created the vibration with and without the GSI bed. So this is the typical case. So this is the block vibration setup, which we operate different frequencies and excitations to come up with the maximum influence one. And then this is the GSI layer, and then this is the typical footing. So we try to model same thing in the numerically as well in Abacus. So this is the excitation. This is the model footing. This is the vibrating block. So if you see the enlarged thing, so we have kind of monitoring the acceleration on top of these red points, and this is the vibrating source. We apply the shaking in these directions, and then we saw the very interesting results. We saw that, okay, before that, how to model the SRM. So what is the material model? We used the hyperelastic model, and we did a cyclic triaxial test and normal triaxial test of this SRM system. And we use the hyperelastic, which is used for the elastomeric bearings and the rubbers. And we saw that it's not bad. It is giving a hyperelastic behavior. We did further triaxial test simulations also in Abacus, which also gives us similar results. So we are fine. So it matches with the experimental data. So numerical model is to some extent is correct. May not be perfect, but it's not way off also. So the model response, if I come back, as I said, it's very interesting. We are very excited to show these results. So this is the without GSI, the top one. With GSI and with GSI GeoGrid, you can see that there is a frequency shift as well as the reduction in the amplitude. And if you compare with the numerical and experimental, we are very happy. You will not get better than this. So what we saw here is we started from the lab scale, then we modeled that numerically, then we went to the shake table, then finally we translated in the field. So all the 3 aspects we have studied in this particular set of case. So what about the liquefaction resistance? Just few slides. I will just conclude my lecture with liquefaction behavior and how it can be used. So if you see, we just casually doing this study, and we're going in detail. I'm not. It's an ongoing work. I'm not having the complete set of results yet. But what we see here is, as you can see with the rubber, so this is the black line is my sand. So you can see the stress path, P-Q stress path. It shows that it's confining stress is becoming 0. But on the same number of cycles, as you increase the percentage of rubber, it is not going towards the 0. So effective stress is not going to 0. So in fact, we have seen the pore pressure development is also less if you have for the SRM mixture. Now the question is, which we don't know, is why, because that is one of the things which is we are now currently studying. macro behavior, it is favorable for decreasing liquefaction potential. We can see this macro behavior. But if you see the micro behavior, we did a lot of, I'm not showing those results. We have done a goniometer study, the particle water interaction study to show that the rubber has a hydrophobic nature. So if you see that the permeability is actually reduces if you increase the rubber. So that means if I go for higher rubber content, the mixture will become less permeable. So again, it is not good for the liquefaction, countering liquefaction potential, right? So one side it is favorable, another side it is non-favorable, but what percentage, quantitatively, which one is playing major role? That's what is the critical, because overall in macro behavior, we have seen that pore pressure development is less if you have a large amount of rubber. So that's what we are now working on it. So before I conclude, a couple of slides to show that there is one application we have started actually. So you see this is a pipe. And then when you apply earthquake, what will happen if this soil get liquefied? So the pipe will be lifted above. So pipe will reach the ground. So it's a liquefaction induced uplift. There are several methods to counter it. One of the method is you just replace that with some kind of high permeable SRM layer, sand rubber mixture. So what happens actually is, like in this part, the water will there will be no pore pressure development because immediately the water will come to the surface. So it will not create any kind of uplift to the pipe as such. So that's one of the things which was hypothesis we have done, and then we try to do that in the shaking table. Same shaking table. If you try to do that in the, let me see whether I can play that in, yeah, I should be able to play that. So here, if you see, so if you see here, this is the without any SRF. So sooner you see that the top part of the soil, so the shake table is now shaking, and you see that there is a quick crack in the soil. Yeah, liquefaction happened, and then there is a uplift. The pipe, there is a PVC pipe inside, and you will see that the PVC pipe will come out. So this is a PVC pipe, clearly came out. You can see that now very clear. PVC pipe came out. So there is not, it's completely the top layer is liquefied. Now, if you see the other one, when I have a top, that on top of the PVC pipe, I have replaced with this drainage, highly permeable sand rubber mix. And if you see that, what will happen? You'll see that the water will come up, everything will be there, but there is no crack in the layer and there is no pipe uplifting is happening. We quantified, I'm not showing the data, we quantified with the strain gauge and the LVDTs, but apparently it is kind of working in the small scale in a shake table test. So that gives us kind of a end of this lecture. I'm not giving any conclusion. I am rather posing you a few questions which is still unanswered. As I said, liquefaction susceptibility of SRM is a question which we have to address. Second question we have to address is, can it be it's used as a sand compaction pipe, because sand is expensive. Whether you can use the SRM instead of SRM piles instead of SCPs. And finally, the how to say, the holy grail of all these things is the constitutive behavior of SRM. Whether we can come up with a comprehensive physics-based constitutive behavior. So far, whatever we used is a kind of a empirical to semi-empirical or a phenomenological model, I would say. But whether it can be a physics-based model possible of this sand rubber mix. These are the questions. I leave it for the audience. And these are the papers you can refer to, which we published over the years on this particular topic. And then, thank you. Welcome to IIT Madras. We live in a very beautiful fauna and flora. And hope to see you soon. Thank you. Yes. I have to agree with that actually. So we use the normal ordinary Portland cement, OPC. So definitely we haven't started with a different cements. but surely it will have some effect. I agree. Well, there are studies on the silty clay. I would say that the degradation behavior will be similar, but only problem in the silty clay is because of its non-plastic nature to some extent compared to our normal marine clay. It might have a stronger, the sharper reduction in the nonlinearity part will be sharper. But these are all my qualitative hypotheses. I haven't done anything, but there should be, I mean, it's worth studying that. So far, we have used 2 millimeter and the less. Yes, there are successives, I mean, kind of later part of the study, which I'm not showing here, it's an ongoing thing. We are start varying the rubber sizes. Yes, it will definitely have an impact. In fact, I would say that the ratio, the governing factor here is the D50 of the rubber to the D50 of the sand. If D50 of the rubber to the D50 of the sand with some threshold value, the behavior will change a lot. It might show you a higher effective, a higher friction angle if you have a sufficiently larger size of the rubber particles. So that is one of the things which we are now studying. No, we all the studies we have considered is under fully saturated condition. So there is no problem with that, because you see, we want to see that how under fully saturated condition it is behaving. So that's, I completely agree, that will be more critical, and all our study is that. One of the things that you may ask is the durability of those rubber under completely saturated condition. That is one of the things that people are asking, and it is the study that someone has to do, and which I personally is not capable of doing at this point, because I am not a chemistry or chemical expert, the durability part of it. So which another issue which before we use it regularly, which we have to clarify by the relevant experts, I would say. Yeah, I mean, direct shear test is, you can trust because its behavior is like a questionless material. I don't see you cannot completely ignore that. But of course, I would say that you cannot, we all know that in direct shear, if you can't do the, I mean, you have not very accurate in the saturated condition. But normally it's a questionless material. It's behavior like a questionless, any of the questionless material. So that's fine with the direct shear. But we have done all direct shear, triaxial, everything, but direct shear is okay, I would say. Yeah, it's a good question. Actually, we haven't really paid much attention to the geogrid strain. See, we had a limitation here. You have to understand, because we are doing a scale model test, in particularly when you do the lab level, we have to fix up the scaling factor. Now, based on the scaling factor of the size of the model and the loading, we scale back to we choose a geogrid which is actually fits the check for exact the scaling. So we haven't really had a chance to vary the different geogrid and see the performance of, like you said, it's one of the things we also in mind, that instead of having 2-layer geogrid, whether one layer is enough. But one of the things you should understand is that it's one thing is the strength of the geogrid. Another thing is the thing that plays a major role is the layer of SRM, which is confined between 2 layers of geogrid, which actually provides in fact, we did the simulation to see that this is 1 layer of geogrid, that is 1 layer of geogrid. In between the SRM is also acting like because under confining stress, right? So it is also acting like a reinforcement, that part of the SRM. So with a single layer, we may miss that benefit. We have to see that, but that's again a hypothesis. Yeah, we have. So again, you are saying that degradation in terms of the durability over the time. So that part we haven't tested. And again, I said that has to be taken by the experts in that field, because I'm not the expert in that particular area. But what we saw in the literature see, if you have a rubber which is mixed with water, it generally doesn't lose its strength for in an ambient temperature. Ambient temperature in the sense, the temperature range they say is about 20 degree to 45 degree. But below soil, more than 45 degree, there may be some effect, which we have not yet started. But otherwise, the degradation as such, in terms of the cyclic degradation in the stiffness, it's almost the similar as it is in the in for the any questionless material.